Čadež, and it's about tidal effects in the vicinity of black holes.
Thank you. Well, this work started many years ago, and I actually ended a few years ago. And the first idea was kind of frivolous. The question was, what would we see if we would throw, let's say, a flashlight into a black hole? What would we see? And then when we looked at this, we found out that, of course, we remember that the tides become very important, especially if you have a small black hole, small mass black hole. And then if we asked ourselves, well, when we saw that if you throw something down the black hole, of course you develop a huge tidal wave. The question was, can this energy from the tidal wave somehow be transformed and be made visible in some sort of a flash or something like that? So here's the outline of the talk. I talk about tides, Newtonian versus relativistic. What is the difference? And we see there is a difference. And then we'll show you some examples of relativistic tidal effect, just kind of theoretical examples. Then we ask ourselves what are the necessary conditions for relativistic tides to occur. And then we'll talk about orbital development toward catastrophic tidal disruption, because you see that, I mean, you have to have kind of special conditions in order to have catastrophic tidal disruption. And then we look at the center of the galaxy and observe transient phenomena of Sagittarius A and their modeling by catastrophic tidal disruption. Then, of course, conclusions. Now, what are kinds of tides? Well, I would say first, sub-resonant tides are something like this. You have a central object and something is going around, and sub-resonant means that the fundamental quadrupole frequency of the object going around the central object is lower than the Fourier, the main Fourier frequency of the tidal field. So I mean, this is only a little bit sub-resonant, because if it would be really sub-resonant, you wouldn't see anything because you wouldn't see the tidal wave. Now then you have, of course, above resonant tides, which is why doesn't it work? Should work, but it doesn't. What about this one? Okay, this one will work. Okay, now if you have very above resonant tide, that means that the tides have much higher frequency than the fundamental frequency of the quadrupole frequency of the object. Then of course all the hydrodynamics is unimportant. Everything that matters is just free falling the gravitational field. So in this case, see, I'm showing this Newtonian pressureless Newtonian tides. And you see what happens in this case. I mean, this object is magnified by 10 times compared to the size of the orbit. You see, I mean, the tides are not very, even if you are very close to the central object, the tides are not very large if you are in Newtonian regime. And Newtonian regime, one thing that's important to notice is that the tides stretch the object kind of linearly as a function of time. Now let's go further, and what are relativistic tides are really quite different. Will you start? Yeah. See, you start with a round object, just like the one, and now you're going toward the black hole with this object. You will see some grid, but which is moving real fast, and you will see that this object is actually stretching extremely fast. You will see that it's stretching exponentially, not linearly, with this kind of time scale. So the object goes toward the black hole just before, like in Newtonian times. See now, now it's stretching, going around. See, color change means that if it's redder, its light is redshifted, and then you see that the scale has changed a lot. So now the object started with a size of 10 to the minus 4 black hole radius, and you see it's stretched to about the size of the black hole. So it has stretched a lot. So this is the huge difference you see between Newtonian and relativistic tides, is that the tidal wave grows exponentially in the relativistic tides, and it only goes linearly in Newtonian tides. So what are then? Suppose there are some phenomena that would be kind of tidal disruption by a black hole, and these are kind of the main characteristics of such phenomena. The rapid luminosity change. Simply why rapid luminosity change? Even suppose you have an object that shines, and because of tides, its area first grows immensely. It becomes long, but its area grows, and because of that, the luminosity grows. So then you have rapid spectral changes due to Doppler shift, increasing gravitational redshift, because the object is going around, and you get spectral changes because of the redshift and because of the Doppler shift. And the time scale of this phenomena is very typical. If you go down the Schwarzschild black hole, the time scale is about 50 gravitational radii, which means that you expect such catastrophic tidal disruptions are very short and very bright phenomena. And the other thing is, of course, a considerable fraction of infalling rest mass energy may be released during the final infall. I'll show you this later why we believe that. We don't know really how the tidal energy is transformed into radiation. We have some guesses that probably a magnetic field must play a crucial role, but this is just more or less a guess. Now, this is where we started. So I just wanted to show how we started this kind of developing this idea. So you will see now kind of a celestial sphere which is illuminated by the flashlight going down a black hole. And you see now the part of the sphere that's toward which the flashlight is going is blue shifted, and the rest is red shifted. Whoops. No, sorry. How do I stop this like this? Now, these are some light curves of this flashlight. And you see, it depends where you observe with respect to the orbit. Now, if you have a black hole and the flashlight is falling down, and if you look in the orbital plane, you will see something very different than if you look above the orbital plane. So these are this is if you look from above the orbital plane and throw down a flashlight, a Schwarzschild black hole, and this is you are in the orbital plane. This is the light curve, and this is this would be the kind of the spectrum, the blue, the redshift, gravitational redshift, and this would be the curve prograde and curve retrograde. And here I have a kind of a little animation. So this would be like theta phi, where you stand. So if I click here, you see I'm looking at the Schwarzschild black hole with theta, I don't know, this would be 0 and this would be 90 degrees, and phi is whatever. So phi goes from minus 180 plus 180 here. So this is what you will see. This coordinate here shows you the redshift. So the light is redshifted and blue shifted a little, and then a little blue shifted and red shifted, and disappears. So the intensity of the line kind of tells you the intensity of the light, and you can see two effect 3 lines. This is the primary, secondary, and tertiary image. Now, if you go, look at from the equatorial plane, of course, the picture is quite different. You can also see what the spectrum would be as a function of time. So I have to make yeah. So this would be the light curve, seen from this position, and the spectrum as a function of time. You can see, the spectrum of let's say, a single line would look something like this, depending how it develops in time. And I think that we can close this now. Now, the next thing was now, okay, let's not look at the flashlight, let's look at the star that we throw down the black hole. Now we have to model the star somehow. As I said before, if you have a catastrophic tidal disruption, then the hydrodynamics is really rather unimportant because all parts actually follow their geodesics. Because the pressure forces are small, relatively small force. So we just model a star by making kind of 1 million particles which have their own temperature. And the deeper they are, the bigger the temperature. So when the star kind of goes around, you will see that each particle moves A, and some particles then, the upper parts then uncover the lower parts, so the star becomes brighter. And this is what it looks like. If you see it from above, you see the star on the right. It's moving toward the black hole, which is in the center of the image. And here on the left, you can see the luminosity. Now you see it starts coming close to the black hole, and it starts being eaten and unwrapped. You can see it's getting brighter and brighter because you can see the inside now. And in our model, I think the luminosity grows by about a factor 10 to the 9. We have to do an extrapolation because this model was rather crude. If you only have 1 million particles, that's not enough to make kind of a real model of a star. But you see, what happens is that if you look at the luminosity of a star, catastrophically tidally started, you don't see any peaks, you don't see any modulation. Why not? Because the star is kind of too big, it gets spread. So, in order to see a peak in the luminosity that we've seen before when you threw the flashlight, you need to throw something really very small. Because if you have any other larger object, it will smear out because of tidal effects. Because it makes a huge tidal tail, and this huge tidal tail smears out, every peak. So I have another one. If you see it edge on, but maybe we can go on. Now, the question is, you see, if you want to throw something like this to get a catastrophic tidal disruption, then what you have to get the object from far on an orbit that goes down the black hole. That means on a highly eccentric orbit. And the question is, and not only that, this eccentric orbit should be such that the object would not fall directly in the black hole, because then you just see something like a book, and nothing. It will look really very uninteresting. So you must have an orbit which makes quite a few turns before falling down the black hole, and this means very precise tuning. And the question is it possible to make this in nature? Can this occur? Now, then you can ask yourself, well, how can it happen? Well, there is a theory, Newtonian theory of tidal evolution, which has been kind of many years ago devised by Huck. And this theory predicts something like this. If you have an object, let's say, orbiting a black hole, then of course you have a tidal interaction there. You have a tidal bulge, and the tidal bulge moves with respect to the star, so it transfers angular momentum from orbit to internal spin. And also it transfers energy from orbit to heat, because the tidal bulge is moving up and down. So what happens usually is, I mean, if you look at the tidal development of orbits in the lambda, which means the angular momentum and energy plane, you can see that, of course, first the energy goes down, but the angular momentum changes a little, because usually the object that's falling in has a huge orbital angular momentum, but very small spin. So you cannot transfer much in spin. So what happens, if you're on an eccentric orbit, then when you come close, the tidal bulge moves with the resonant frequency of the object, so it rotates rather fast. And then it may be rotating faster than is the orbital frequency. In this case, the object has more spin than it would have in the resonant orbit, which would be a circular orbit where the tidal bulge would always point in the same direction toward the center star. So in this case, if it's faster, so if you start with an eccentric orbit, and if you are too fast, then when you reach a minimum of energy, you take the energy from spin and take the object out, away from. So you make the angular momentum larger, but if you don't have enough angular momentum in spin, but then also you see when you get very close, then the moment of inertia, if you become resonant, the moment of inertia becomes larger, because the object, the tidal bulge becomes large, so which increases the moment of inertia. And in this case, you go down like this. You decrease orbital momentum, and you decrease energy. And here you see what happens with the orbit in this case. See, you start with a circular orbit, and then the orbit goes down, 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 and in the end, you go down the black hole. But here is, I think, what I find kind of interesting. Here I'm showing the effective potential. This is the Kepler effective potential. This is the Schwarzschild effective potential for moving around this black hole. And you see the Keplerian effective potential has the minimum here, and it has no, just one turning point. But the Schwarzschild Kepler effective potential always has two turning points. No matter how close you go, it has two turning points. So actually the star feels the potential between this point and this point. But at a certain moment you will see that because this turning point disappears, because you have a peak here in the potential. And when this disappears, the star that fills in this gap here has a huge energy available. Which means, what is this energy? This is the energy of the tidal wave that can be somehow liberated and turned into something else. So let's go on. Now, what are the necessary conditions for catastrophic tidal disruption to occur? Actually, there are three, and they're kind of very simple. One is that the star should be much smaller than black hole radius. Well, no, it should be smaller than black hole radius. Otherwise, suppose you have a solar mass black hole hitting, kind of interacting with the sun on a very eccentric orbit. Now, what would happen? This black hole would just go through the sun. It would eat a little bit, but then, so it would not make a complete tidal disruption. Of course, it would look catastrophic, but not very catastrophic in the sense that you would not expect like mc square of energy released somehow in the tidal wave. And of course, the other thing is, of course, the Roche radius has to be larger than the black hole radius, because otherwise the tides are not sufficiently strong to destroy the object before it falls down the horizon. And of course, you need high angular momentum of launching orbit, and I think I've shown you that this high angular momentum somehow can be provided by the tidal evolution of the orbit. Now, so these two conditions make kind of boil out to this condition, that the escape velocity from the object divided by c squared should be mass of the star over mass should be larger than mass of the black hole squared, and the third power of the escape velocity over c should be smaller than mass of the black hole. So there's a range of masses for a given black hole which can produce catastrophic tidal destruction, depending on the Roche radius. So let's see what this means. So I've just here plotted. You see, this is the region where tidal disruption would occur. For a mass of the black hole would be 4 solar masses. And these are, kind of, this is the main sequence. This is Betelgeuse, these are the planets. And here I have plotted asteroids. Each asteroid has 2 points. One point corresponds to an asteroid that would be liquid, somehow, liquefied. And the other one is for a solid asteroid, because solid asteroid, solid state forces make the asteroids very strong compared to what it would be liquid. So, but you see, solid asteroids are in here, so they. This is solid and this is liquid. Now let's go for a larger mass, 40 solar masses. See, but no star, you see, no star, almost nothing, only asteroids can be totally tidal disrupted by, let's say, 40 solar mass black hole. Let's go, if we go further, we go to this, I think this is 40,000, yeah. This would be the center black hole in our galaxy. It's 4 million, and you can see like planets could be catastrophically disrupted. But the asteroids are they are too dense, but you see, if they were liquid, they would be catastrophically disrupted. So the question is, can they become liquid? And I say, yes, they can become liquid. Why? Because asteroids, as I described before the tidal disruption, they would go close to the black hole and would develop a tidal wave. And this tidal wave would heat them up, like like the tides heat Io, the Jupiter's moon. And so they can heat it enough to make it liquid. When it makes it liquid, you see, it can become catastrophically tidal disrupted. So they really fulfill the conditions of this Hut's mechanism to go down the black hole and be tidally disrupted. So, so here I've just described this tidal evolution, a little bit more in detail. this is the eccentricity of the orbit, and this would be the periastron distance in terms of the Roche radius. So if you see if you come below the Roche radius, then, and if you are liquid, then you can go down. Your orbit develops like this. Now here I just wanted to show you that what are the time scales. The time scales for an asteroid. You see, now asteroids, you have what kind of time scales do you have to have? First, the asteroid must start below its liquid Roche radius, but above its solid Roche radius, close to the black hole. And then it must be heated, but it must, you see, it must have enough time to, because when it comes close, it's heated, but when it goes far away on an eccentric orbit, then it cools down. So the heat must stay long enough in the asteroid produced that it will melt. So if a small asteroid will not melt, because it will cool down when it's far away, because its thermal relaxation time is too small. So I guess I will go on. Now this is the galactic center showing the number of stars. And the idea is the galactic center has enough stars that we think that it has enough asteroids and maybe planets and so on that they can be sufficient to describe the galactic flares. Since I don't have time, so this is the distribution of stars, of B stars in the center of our galaxy. And the idea is, we know that our sun has about 10 to the 8 asteroids of the size up to 10 kilometers, which would be perfect to make galactic flares. Now, this, I just found this movie, it's really impressive. See, this is a light from a past tidal disruption of a star by galactic travel. So they have just made images of the center galaxy in infrared, and you can see actually this is light traveling. I think maybe a few hundred years ago there was a tidal disruption of a star in the center of our galaxy, and this light echo is moving through the center of the galaxy. So apparently tidal disruptions do occur at the center of our galaxy. And now here I show some pictures from, like Trippe et al. About light curves of observed galactic flares. And you can see what is interesting here. You can take the Fourier spectra of those light curves, and this region of the Fourier spectra, in this region is the region where we actually expect the peaks to occur. You can see the peaks. So you see the asteroids falling down the black hole are almost like flashlights. They are not elongated very much. They are not smeared out, but they make peaky light curves. And just for the end, I just wanted to show you. See, all those. They are very similar, those flashes, and we modeled two of them with kind of a very, very basic model, and you can see the fits are, say, fairly good. And I guess this is, yeah, well, now there's just maybe one idea how, I don't know how the energy of the tidal wave is transformed into radiation, but it must be somehow. So the idea is that maybe it's by growing magnetic field, and you see what happens to the magnetic field. So I just calculated a simple model. You start here. This would be the central pressure of a liquid asteroid. This would be the kind of the center magnetic pressure. If you assume the so-called magnetic Bode law for the magnetic field of an asteroid, and then as time goes on, you see the central pressure goes down, and the magnetic pressure goes up. But this line represents the well, this is the central dynamic pressure. I'm sorry, this central dynamic, and this is pressure. This is the pressure of a static round asteroid. So at a certain moment, after about 40 minutes, you see the magnetic pressure is larger than the dynamic pressure, and in this case, now I think at this point you would have a magnetic field, taking action. So that's why I put question marks, because I don't know what happens. So the model would somehow break down. Somehow the magnetic field could not probably increase, to 10 to the 10 Tesla like here, but probably less. But somehow I think that that's an indication that there is enough energy to produce, and this is just an image how the magnetic field would grow. This would be the magnetic potential as a function of time when this asteroid is being stretched. And it's, I think, thank you.
Okay. Thank you very much.